Hi calculus students. This video has solutions for the even numbered problems from section 8.2, integration by parts. So I'm not going to go back over the how-tos of this. We're just going to jump right in. I'll just say that remember there's two methods. If you can do the little tic-tac-toe method shortcut, then that's great. You definitely want to do that. And the first few, I think, are ones where we can do that. Just kind of scanning through the problems, which is never a bad idea. It looks like 2 through 8 are going to be tabular integration style problems, and then from 10 onward, 10, 12, 14, 16, and 18, looks like we'll have to do the whole UDV setup. Alright, so let's get into it. So there's my algebraic and my exponential. And remember, here we're taking antiderivatives, so that's going to be 1/3 e to the 3x, 1/9 e to the 3x. Don't forget to alternate your signs. So it looks like I've got 1/3 x e to the 3x minus 1/9 e to the 3x plus c. And just check as we go. That looks great. Alright, number 4. Another tabular problem. Remember, you have to take these derivatives till you get to 0, which is why it only works with these algebraic types. Missed my lining things up a little bit there. It's alright. Alright, that looks good. Okay, so minus 1/2 x squared e to the negative 2x minus 2 times 1/4 is 1/2. 2 times 1/8 is 1/4. Right? And we'll just give that a check. Looks good. Number 6. X and cosine 2x. So antiderivative of cosine is positive sine, and antiderivative of sine is negative cosine. So alright, looks good. Number 8. Derivatives and antiderivatives. And let's just check that. All right, all looks good. And now on to the, well, how should we call these? The ones where you really have to use the recipe, right? And that Liate. Okay, so you have that handy by you, I hope. And number 10, we have an x to the 1/2 times natural log x. So the logarithms always come first, and then try to remember to include the dx there. So the derivative of this is 1 over x dx. Antiderivative here, bump the exponent up 1, and then divide by the new exponent. Should get you this. So the rewrite of this is uv minus the integral of v du. And multiplying by 1 over x is going to bump that down 1. So that part's done. And then minus here, so taking the antiderivative here, bump the exponent up 1 to 3/2, divide by the new exponent. So that's going to be minus 4/9 x to the 3/2. And let's check that. Good. All right. This one's real similar. Remember, the whole reason why we love rational exponents so much is because they're so calculus-friendly for doing derivative rules with and antiderivative rules. So let's see how different the answer turns out to be here. So still, here's my natural log here, 1 over x dx, and then here, x to the negative 1/2. Bump the exponent up 1, and then divide by the new exponent. So the rewrite looks like uv minus the integral of v du. So let's see, if we take the antiderivative of this, bump the exponent up 1 to 1/2, and divide by that, dividing 1 by 1/2 is the same as multiplying by 2. And checking that answer. What number is this? Oh, 12. I'm looking in the wrong place. Yeah, there we go. Yep. Looking at something with a tangent inverse in it. All right, how about number 14? So that's interesting because it doesn't have two different things there. There's just one thing. So it must be, if the suggestion, because it's in this section, is that integration by parts is going to work. If we were going to try that, then it would have to be kind of like the trig inverse examples. The only thing here to make dv is the dx. So let's try that and see if it works. Derivative of this is 1 over x squared plus 4 times the derivative of what's inside. The v would just be an x. And let's see what the rewrite looks like. So uv minus the integral of v du. All right, well, this is a little bit tricky to deal with, I think, because I'm not sure that you have seen, I feel like we'd be better equipped to deal with this after we get through section 8.5. But I'm going to tell you what you need to do with this here. I'm going to give you a little hint, and then I'd like you to pause and continue from there. So here, what do you do with this? Well, first of all, we can move the 2 to the outside. Let's just do that. Now, there's no u substitution or anything that can work here. If you u substituted this, the x squared plus 4, the derivative of that is 2x. There's x squared on the top, so it doesn't work out there. So here's what we're going to do. This is a division problem, x squared plus 4. We're going to actually do long division here. It's been a long time since you've done that, I bet. It's not a very long division problem. It's a very short long division problem. So remember how to do this? I think about it not so much as dividing, but figuring out, like, what would I have to multiply this by to get this? Well, 1. So 1 times this whole thing now, x squared plus 4. When you do long division, then you subtract this. So those cancel out. If you picked the right thing here, then those should always cancel out. And then distributing this, that's minus 4. And that's there's nothing else to drop down here. We're done. That's the remainder. So it's like minus 4 over this. Minus 4 over x squared plus 4. So this right here is the same as this. So we need another rewrite, and I need to give myself a little bit more room. All right, then I got minus 2 times the integral 1, and I can separate that into 2 separate integrals, 1 dx minus 4, I'm just taking that 4 to the outside because I don't want it to be there, 1 over x squared plus 4 dx. Okay, now you have to look at that and think, well, that kind of looks like tangent inverse, where you want it to get it to match up to 1 over 1 plus u squared. But if you're trying to get it to match up to this, that is not negotiable. That has to be a 1. So I need to factor that 4 out. So let's see, how shall I do this? I think I'm just going to do this right here, this part of the problem. Actually, I'll bring the 4 too. So there's a 4 there. Now I need to factor this, a 4 off the bottom of this, which leaves x squared over 4 plus 1. And then the 4 that I factored out of this, I'm going to bring to the outside. So those cancel out. It's equal to 1 over, and now if I make a u substitution, if I let u squared equal x squared over 4, then u is going to be x over 2, and du is going to be 1/2 dx. Okay, so that means I need a 1/2 in here, which means I need a 2 on the outside. Now those 4's canceled out, but I'm still going to end up with that. And that gets this into the right form. And that's equal to 2 tangent inverse of u. Okay, so I think we're there now. If you're thinking to yourself, whoa, this is crazy. Yeah, this is a pretty crazy one. but this can happen. So let's see if we're ready to just write the final answer. Okay, so minus 2 times here, the antiderivative of 1 is just x, so minus 2x. And then here, this whole thing with the 4, I did take the 4 with it, is equal to this. So I have minus 2, and then this minus sign cancel. The 2 times 2 is 4, tangent inverse, x over 2, plus c. All right, with some small amount of trepidation, I'm going to look and consult the solution manual. Yes, we got it right. So, I mean, that's crazy. That means that if you took the derivative of this, which involves product rule here and chain rule, and then just that random minus 2x, and then the derivative of this with all the craziness of tangent inverse and the chain rule there, that somehow the derivative of this simplifies just back to that. Pretty crazy. You can try it if you don't believe it. That is definitely as hard as these problems ever get. And you're certainly not likely to see something like this as a multiple choice question, you know, that you're supposed to be able to do in like 2 minutes. Obviously not. So, don't get too scared about that. Let's see, 16. We have cosine inverse of 2x. So I know that if I have some function, like for example, if I wanted to take the antiderivative of cosine of 2x, the antiderivative of cosine is sine, and then because there's a 2 in here, it's just a constant multiple. I just have to do that. So rather than do the cosine inverse of 2x, I'm just going to do the antiderivative of cosine inverse, and then I'm going to use this general rule about when there's a 2x on the inside. So what's the antiderivative of cosine inverse x dx? And then I'll adjust my answer and say, oh, well, if that's the antiderivative of cosine inverse of x, then cosine inverse 2x would just be, and then do that trick. Okay, so let's see. So u is going to have to be the cosine inverse of x, and dv is just going to be dx. Got to know those, right? Okay, so what does the rewrite look like? The rewrite of this is uv minus the integral of v du. Now du has a minus sign on it, so that's going to flip that. Alright, so this is going to play out similar to the sine inverse problem that we did in the last set of homework problems, where to do this, I need to let u equal 1 minus x squared, so du is equal to minus 2x, so I need a minus 2 here, which means I'm going to need a minus 1/2 out here to balance. So, once I have that, my x cosine inverse x is still there. And now here I have minus 1/2 times the integral of u to the negative 1/2. Right, just doing that plain old chapter 6 u substitution. And the antiderivative of u to the negative 1/2, bump the exponent up 1 to u to the 1/2, divide by the new exponent, that's going to cancel that out, so it's minus u to the 1/2. And the u is that. Let's check that out. Just cosine inverse. Oh, we didn't do the last, so that's just the antiderivative of this. So if you wanted to do the antiderivative of cosine of 2x, then so long as you know what the antiderivative of cosine inverse of x is, it's just that whole thing with the 2x's plugged in, so that'd be 2x cosine inverse of 2x minus the square root of 1 minus 2x squared plus c. And then because it's a 2x, just a constant on that, the whole thing needs to get multiplied by 1/2. Well, that's good. You can distribute the 1/2, whatever you want to do with that. Does it matter if the c is inside or outside of these parentheses? No, it doesn't, because we haven't solved for c yet, so some constant that I don't know versus half of some other constant that I don't know what it is yet, so it does not matter. Okay, I think we're up to 18. Right? Pretty sure. All right, 18. X tangent inverse x. So that comes first in the Liate. That's inverse trig. So u is going to have to be tangent inverse x. And that's my derivative of tangent inverse, and the dv is just going to be the dx, so v will just be equal to x. So let's see what the rewrite looks like. We got x times the tangent inverse of x, that's uv minus v du, integral of v du, that is. And that's going to work for a u substitution, because I've got second degree here and first degree on the top. So let u equal 1 plus x squared. Du is 2x dx. Got the x there, I need a 2 here, and then a 1/2 there to balance it. So x tangent inverse x minus 1/2 is the integral of 1 over u du, and antiderivative of 1 over u is natural log u, and the u is 1 plus x squared. Should you put that in absolute value signs? You could, but in this case, if you square a number, that's going to be positive, add 1. These are all positive, so you're actually okay not to do that. Let's check that answer. 18. Huh. Oh. I messed that up, didn't I? Because I treated that like I just found the antiderivative of tangent inverse. I did not find that has an x there, so I messed that up. So this is x dx. I just ignored the fact that that was there, which means that this is x squared over 2, which means that that's x squared over 2, and this is minus, actually that 1/2 is in fact there. It would be that, and then we're going to do a big scribble job on all of this. And let's see, so this is going to be like, was it number 14, where we had to do a little long division to clean that up? So x squared plus 1 into x squared goes 1 time x squared plus 1, subtract that. minus 1 over x squared plus 1. Well, the good news is once I rewrite it like this, I actually don't have to do any more u substituting. So if you're looking for some good news in the middle of this differentiation, anti-differentiation quagmire. Okay, so we're looking for the antiderivative here. This rewrites to 1 minus 1 over 1 plus x squared dx. And I think we're just good to write the final answer now, because the antiderivative of that is tangent inverse. That's just a we recognize it kind of situation. So I've the antiderivative of 1 is x. So I've minus 1/2 x, 2 minus signs here, plus tangent inverse of x plus c. All right, let's see if that matches up. Yes, it does, except for forgot to distribute that 1/2 to that. All right. And, you know, you could collect those together and factor the tangent inverse out, whatever, but you don't need to. All right. That, I think, takes a silver medal here for most difficult / annoying ones of these problems. Now we're jumping up to 30 to 34. And the difference with these is we have limits of integration. So we're actually going to get a number answer. So the first one, I've got one that is going to work with tabular integration. So that's x 1, 0, minus 1/5 e to the negative 5x, 1/25 e to the negative 5x. And that's going to give me an antiderivative minus 1/5 x e to the negative 5x minus 1/25 e to the negative 5x. And where are we going? From 0 to 1. So plugging 1 in gives me negative e to the negative 5 over 5 minus e to the negative 5 over 25 minus plugging a 0 in here knocks that out. Plugging a 0 in here gives me minus 1/25. And I'm not going to simplify that. Okay, number 32 looks like we need to do, let's make our u equal to natural log x, because logarithms always come first. And then the dv is going to have to be x to the negative 2 dx. The antiderivative of x to the negative 2 is bump the exponent up 1 and divide by the new exponent. So my new version of the problem is uv minus the integral of v du. Now that already has a minus sign there, so that's going to flip that. And then I got 1 over x and 1 over x. Right? And this is a definite integral, going from square root of e to e. Now this already is antiderivatized. Okay, so antiderivative of this, bump the exponent up 1, x to the negative 1, divide by the new exponent. So my whole antiderivative, I'm going to rewrite that because I'm going to start plugging in numbers now. That minus 1 over x. I can finish this on this page. I think I can fit it all in there. And also, I don't know, you could, if you wanted to, factor out a negative 1 over x times natural log x plus 1. That might be easier to deal with. So plugging e into that gives me negative 1 over e times natural log of e is 1 plus 1 is 2, minus plugging the square root of e into this is minus 1 over the square root of e times the natural log of e, the square root of e, that's the same as e to the 1/2. Natural log of e to the 1/2 is just 1/2 plus 1 is that. And I'm not going to simplify that answer from there. I'm going to try to get one more last problem done here. And since I already know, I've already done that sine inverse problem, right? Let's see. Where is it? And you should have in your notes. So there's no reason to be doing the sine inverse one again if you have already done that. I guess you could do it for practice. But let's see if I can just find it. The antiderivative of sine inverse x dx. You can leave that open, please. Oops, that message did not get through. Hold on one second. I'll be back. The antiderivative of sine inverse of x is x sine inverse x plus the square root of 1 minus x squared plus c. So I'm going to use that fact because I already have done this problem before. And now I'm just doing this integral from, what are my limits of integration? 0 to square root of 3 over 2. So I've got this expression. From 0 to square root of 3 over 2. So I'm just shortcutting the process of doing all the work for that again. You can refer back to your notes. Or you could practice if you feel like you need to practice doing that. Okay, so plug in the square root of 3 over 2 in here. That's square root of 3 over 2 times the sine inverse of the square root of 3 over 2 is pi over 3 plus the square root of, when I square that, I get 3/4. 1 minus 3/4 is 1/4, and the square root of 1/4 is, well, I guess I have simplifying still to do, so I'll just write that like that for now. So that's what I get when I plug in that, and then minus, what do I get when I plug in 0? Well, the 0 is going to knock that out, and then that's just going to be 1. So there's not really a whole lot of simplifying left to do here, except that maybe you could write this. The square root of 1/4 is the same as 1 over the square root of 2 or a square root of 2 over 2, if you want to recognize that as a common trig-like value. And let me just check that here. Oh, just kidding. This is the square root of 1/4 is just 1/2. Sorry. There we go. That's fixed. And so that 1/2 minus 1 is minus 1/2. And that's good.